Here is a combined summary of the 4 pages. Reionization, a pivotal phase in the universe's evolution, remains poorly understood due to the intricate interplay of astrophysical processes. This study employs Gaussian Process Regression, GPR, to learn about reionization history and infer astrophysical parameters in a model-agnostic way. The authors reconstruct the UV luminosity density function using Hubble frontier fields and early James Webb Space Telescope data, and compute the global differential brightness temperature fluctuation during reionization. The reionization history is influenced by various astrophysical parameters, including the clumping factor CHII, ionization efficiency Xi-ion, and escape fraction FESC, which are poorly constrained by observations. The authors highlight the degeneracy between Xi-ion and FESC, which can lead to significant variations in the magnitude average product of these parameters, affecting the validity of cosmological models inferred from reionization data. The study delves into the realm of reionization and its observables, focusing on the 21 cm cosmology. The global brightness temperature fluctuation is a key observable, with the total brightness temperature at redshift z given by the difference between the spin temperature and the background temperature. The differential brightness temperature can be calculated at any spatial point, and its Fourier transform is denoted as delta Tb, k. The paper discusses the instrumental noise power spectrum in k space, given by the equation Pn21, z, which depends on the antenna array's baseline, observation time, and other instrumental specifications. A full Bayesian Markov chain Monte Carlo analysis is performed to explore the role of existing datasets in predicting the observationally favored bounds on the reionization astrophysical parameters. The authors predict the UV luminosity density profile and then use this profile to obtain the reionization history as a function of redshift. This study focuses on reconstructing the UV luminosity density function in the redshift range z tilde operator 4-12 using Gaussian process regression. The methodology involves defining log10 rho UV in 4 distinct nodes and taking them as free parameters in MCMC sampling. By solving the ionization equation, treating Fescinto Xi-ion as a single parameter, and applying a uniform prior on log10 Xi-ion, the research aims to forecast astrophysical and cosmological parameters from 21 cm power spectra. The clumping factor is initially treated as a free parameter but is later fixed at Xi equals 5 for a comparative analysis. The reconstructed UV luminosity density profile is shown in Fig. 1, indicating consistency with the logarithmic double power law model within the redshift range 4 less than z less than 8. For z greater than 9, the mean reconstructed curve deviates from the best fit values but remains within 2 sigma uncertainties. The study also compares constraints on astrophysical parameters using different datasets, as shown in Figs. 2 and 3, highlighting the impact of the clumping factor on the results. This novel approach simultaneously trains the parameters governing the GP mean function and the kernel hyperparameters to obtain the predicted UV luminosity density profile, providing new insights into the cosmic reionization history. This research paper employs a Gaussian process to reconstruct the evolution of the UV luminosity density, exploring the reionization history of the universe. By combining 2 data compilations, UV17A and UV17B, with QHII and Planck datasets, the study analyzes the ionization fraction QHII and the global 21 cm signal at the reionization epoch. The results indicate a positive correlation between the parameters log10, Fescion, and CHII, and an anti-correlation with Trek, the recombination time. The reconstructed UV luminosity densities differ between the 2 data combinations, but at Z3, the average values are similar, indicating an unchanged correlation between parameters when fixing CHII. The study reconstructs the reionization history profile using the obtained bounds on the parameters log10, Fescion, Chi, and log10, rho 14, and derives the evolution of the ionization fraction via equation 11. The reconstructed QHII profile is used to trace the nature of the 21 cm differential brightness temperature delta Tb, employing equation 4. The paper compares the constraints obtained on the astrophysical parameters using different dataset combinations, presenting the results in figures 5, 6, and 7. The analysis is conducted through Markov chain Monte Carlo simulations to obtain the mean and 1 sigma bounds on astrophysical parameters. The results indicate that the inclusion of SARAS data provides more precise constraints on the astrophysical parameters and better constrains the reconstructed reionization history and global differential brightness temperature profiles. The study forecasts the reionization power spectrum of 6 Lambda CDM parameters with 2 astrophysical parameters using different dataset combinations, showing that the inclusion of SARAS data and fixing the clumping factor CHII to a constant value of 5 improves the constraints on the astrophysical parameters and the cosmic reionization history. The research paper explores the application of Gaussian Process Regression, GPR, to reconstruct the reionization history of the universe, leveraging data sets like UV17, A, UV17, B, Planck optical depth, and QHII alignment alpha. The analysis demonstrates the effectiveness of GPR in improving bounds on astrophysical parameters during reionization. Furthermore, the study presents a 21 cm power spectrum analysis, which, with future SCA data, is expected to improve bounds on 6 cosmological parameters and 2 astrophysical parameters. The paper also delves into the role of high redshift galaxies as probes for cosmic reionization, highlighting their importance in understanding the interplay between radiation and the intergalactic medium. It discusses the use of machine learning algorithms in identifying and predicting properties of these galaxies. The authors emphasize the need for further studies on the interplay between radiation and the intergalactic medium, the role of high redshift galaxies, and the development of more sophisticated machine learning models. The research on pages 17 and 18 delves into astrophysics and cosmology, focusing on dark matter, dark energy, and the early universe. It discusses various methodologies including numerical simulations, observational data analysis, and theoretical models. Key findings include the implications of dark matter on galaxy formation, the role of dark energy in the universe's expansion, and constraints on cosmological parameters. The early universe is also examined, covering topics like the cosmic microwave background radiation and the first stars. The authors utilize numerical simulations and statistical analyses to support their arguments. This research emphasizes the importance of understanding these phenomena to comprehend the universe's evolution and structure.